Just starting with this one, you've got. He's saying that many organic compounds. I have this thing, the division chart with me. Okay, so starting with this thing, many organic compounds, including alcohol. So basically, he's just asking for what will be the structural formula of the products that's going to be formed. So starting with the first one, okay, we're going to pick the first one. Start with that. That's a secondary alcohol because it's 3 carbon atoms and 3 H's. The middle one has an OH. So that's a secondary alcohol. And what is he doing? He's adding a reducing agent to it. Now, if you look at the chart, secondary alcohols can't be reduced. Remember this, that when you have an alcohol, alcohols can be oxidized, like primary alcohols can be oxidized. You can have oxidation and they can turn into aldehydes, which can further be oxidized by toluenes, and you can turn them into carboxylic acids. And secondary alcohols can be turned into ketones by oxidation by KMNO4 or K2Cr2O7. But you can't reduce an alcohol. I mean, the ketones can be reduced back to alcohols. The aldehydes can be reduced back to alcohols, but you can't actually reduce an alcohol. So there's not going to be any reaction in this case. There's going to be no reaction in the first one. So then the next one. This one is a ketone. Like if you look at this, it's CH3. And the C double bond O is on the middle carbon atom. So that one is a ketone. So it's on the middle carbon atom. And he's trying to oxidize it with toluenes reagent. So remember that aldehydes get oxidized. This is toluenes reagent. So aldehydes, they do get oxidized by toluenes reagent. Not ketones. I mean, ketones don't have any further oxidation. I mean, they do have a reaction and they form cyanohydrins, but that's a reaction with both aldehydes and ketones. So there's no further oxidation for a ketone. Like the reactions, basically, they stop at ketones. No further oxidation of ketones. So again, this one over here, there's not going to be any reaction. TK, is this clear? Clear, Alicia? Anna, is this clear, Nabila?
Yes.
So then you've got this one. This one is an ester. And he's saying that he's warming it with KOH aqueous. Now remember, we can quickly cover esters for a second. I mean, what's the situation with esters that if I open the board, and we had I mean, we were doing carbonyl compounds, but I'll just cover esters quickly, which you've already done in O-levels as well. So the thing with esters is that it requires an alcohol and a carboxylic acid to form an ester. So we can quickly do this. You need an alcohol. Okay, that's one thing. And you also need a carboxylic acid to go along with it. And together, if you react them together, it's going to be a reversible reaction. It can go both in forward direction or backward direction, depending on the conditions. An ester molecule is going to be produced, and a water molecule is going to be produced. To form an ester, the conditions that are required are concentrated H2SO4, and you also need reflux with it. And if you want to break an ester, it's going to be dilute. There are two types of hydrolysis: dilute acid, mostly sulfuric acid, plus reflux, or it could be a dilute alkali, mostly it's NaOH, plus reflux. So to form an ester, that's a condensation reaction. If you want to form an ester, it's known as a condensation reaction. And to break an ester, that's known as hydrolysis. Basically decomposition with water. So I'm going to try and form an ester. First thing, what are esters? Esters are those substances with fruity smells. They're sweet smelling. They are oily substances, and you use them in perfumes and food flavorings. So perfumes, you make perfumes out of them. You make food item out of that. So most of the artificial food flavors and sweeteners are basically esters. Anyway, so let's start with the first molecule. It's kind of the same as O levels. If you take an alcohol has an OH group. It's got this one is ethanol. So all these are H atoms. And you need a carboxylic acid. So let's take a 3-carbon atom carboxylic acid. Carboxylic acid has double bond ON. OH. The two functional groups are going to react with each other, so they should be facing each other. And what happens is that the carboxylic acid loses its OH and the alcohol loses its H, and they turn into water, which is why it's known as a condensation reaction. So water molecule is formed, and the two molecules kind of join in. I mean, the middle part goes missing, and the two molecules, they basically end up joining together. So I'm just going to remove the middle part. That is going to go, and the two groups will come together, and they'll join with each other with an ester link. So the linkage that's formed in the middle, that's known as the ester link. So that's known as the ester link. You should know how to name this molecule. The molecule is named in two parts. When you try to name the molecule, what you do is you split it up into two parts. This side has 3 carbon atoms, so that's prop. This side has 2 carbon atoms, so 2 carbon atoms is eth. The alcohol side would be referred to as vial, and the carboxylic acid side would be referred to as, or the double bond O side would be referred to as O8. So this one is going to be known as ethyl propanoate, and that's the name of the molecule. So that's how esters are going to be formed. So that's one reaction. So just remember that the carboxylic acid and the alcohol, they must be in front of each other, and they're the ones that are going to react. And when you want to break an ester, it's going to be exactly the reverse. So if you want to do so this is making an ester. If you want to break the ester, all you have to do is you break the ester link, and it's all exactly the reverse. So here's a molecule. So just 1 minute for the azan.
Sir,
Yes.
so you can't just add water for it to become an alcohol?
I mean, that is basically what you do, but you need to add an alkali or an acid. Okay.
Yeah, thank you. So what does reflux actually mean?
It means this thing. Not reflux chemistry. So it means this thing. So basically, what you do is when you talk about reflux, what that means is that you want to heat a substance, but the substance is volatile, so it kind of evaporates. To prevent it from evaporating, you put a condenser on the top. Is that clear?
So it's like wait, the the fractional distillation thing.
No, but it's, I mean, you want nothing to escape. Like if molecules evaporate, you don't want them to escape. You want them to go up and then fall back and condense back. Is that clear?
Yeah, thank you.
Acha. Just wanted to write one minor point over here is, and so that point is, take it just a second. So now the thing is, when you hydrolyze an ester, you break it down into its into an alkaline carboxylic acid back again. You do the reverse. You heat it with a dilute alkali or dilute acid. Now the thing with alkaline hydrolysis is that instead of the carboxylic acid, what you're going to get is, under alkaline conditions, the NOH or whatever alkali that you're using, it's going to end up reacting with the carboxylic acid to form a salt. So you're not going to get the carboxylic acid, and that is true for under alkaline conditions only. Okay, so you have to be careful with this. Like carboxylic acid and alcohol, they react together to form the ester, but when you break an ester, acid hydrolysis, you get the two things. But if you do an alkaline hydrolysis, you're not going to get a salt, you're not going to get the carboxylic acid, you'll get a salt of the carboxylic acid, because the alkali would end up reacting with the carboxylic acid. So make sure you remember this point. So that's all about esters. You should know how to make it, you should know how to, when it's going to form, and how to break it. But be careful, alkaline hydrolysis results in the formation of the salt of the carboxylic acid, which are also known as soaps, not the carboxylic acid itself. Now, coming back to this, he gave us this molecule, which is CH3, CO2, CH, CH3, and he's saying, what are the structural formula of the organic products that are going to be formed? So, so this molecule, the first thing is you have to figure out what this molecule is. It's CH3, and then there is CO2, which is C double bond O and O. So it's CH3, CO2, and then there is CH, so C with one H, and then it's got two CH3s. So there's a CH3 and there's another CH3. Now here's an ester link. It's clearly an ester. He's saying you're heating it with an alkali, KOH aqueous, and you're warming it. So the ester is going to break. This part will turn into a carboxylic acid. It will become CH3, C double bond O, and OH. And this part over here, it will turn into an alcohol. So it's going to be CH3C. There's another CH3. At the bottom, there's a CH. And there's an O, and it will become OH. Okay, so you're going to get these molecules. Add in the OH and the H back again, and you'll have carboxylic acid in this thing. So all you have to do is, now there's one mistake I made, and I just told you that when the conditions are alkaline, you're not going to get the carboxylic acid. Instead, you're going to get a salt of the carboxylic acid. And that's how salts of carboxylic acids are formed. Remember this, we'll just quickly do this as well. Remember this. I mean, that's the only thing you pretty much need to know about carboxylic acids is that they are acids. Whenever you have a carboxylic acid, it's basically C, double bond O and OH. So what it does is that it tends to lose the H plus one in the OH. It's always the OHH that is lost because that's a highly polar H. So it's going to be RC double bond O and O minus one, and the H would break down. And it's a weak acid, so it's going to ionize partially. So just remember, it's always this H that's going to be lost. And whenever the carboxylic acid, which is a weak acid, it reacts, it has all these acid reactions. What are these acid reactions? A metal can react with an acid to produce what? It's going to produce, okay, let me write the acid first. An acid would react with the metal to produce salt plus H2. So it's going to produce salt plus hydrogen gas. So I've got a carboxylic acid. I'm going to write the condensed version of the formula. If I reacted with, let's say, Mg, remember how a salt is produced. The H in the acid is lost and it gets replaced by Mg. That is what's going to happen. So the H in the acid will get replaced by Mg. So it's going to become RCO minus 1. And Mg would be group 2, so it's 2 plus. So the formula of the salt is going to be, if you do crisscross, it's going to be this. Plus hydrogen gas is going to be released. And you can balance this equation, it's going to be 2 RCOH. So always remember the salt is going to be produced in the same way. That's reaction number 1. Then you've got another reaction, which is that the acid reacts with bases, which are metal oxides and metal hydroxides, or metal hydroxide. So when they react with bases, what is produced is they're going to produce salt plus water molecules. So I'm going to take an example of, let's take the example of ethanoic acid. So that's CH3 and COH, C double bond O and OH. You reacted with the base NaOH, and a salt is produced, which is going to be, in this case, CH3, CO minus 1, and Na plus 1, plus water molecule. So remember, it's always the carboxylic acid H that gets replaced by the metal ion. The third reaction is you've got a reaction. What other reactions do acids have? The third one is acids react with carbonates as well. So acid plus carbonate produces salt, water, and carbon dioxide. It's not just a carbonate, it's a metal carbonate or an ammonium carbonate. So an acid plus a carbonate would produce salt, and it will produce water, and it will produce carbon dioxide just like any other acid. So I've got an acid. Let's talk about methanoic acid. Methanoic acid has only 1 carbon, so it's double bond O and OH. So let's say it reacts with calcium carbonate. So how is the salt going to be produced? The COH loses the H, and that gets replaced by the metal ion, which in this case is calcium. So it's going to become H, C double bond O, O minus 1, and Ca is plus 2. To balance out the charges, if you do crisscross, it's going to be 2. This would be twice. Plus water plus carbon dioxide is going to be produced. You could have written this as HCOH, and this could have been written as, in the condensed form, it would have been written as HCO minus 1 twice, and C is 2 plus. The fourth reaction that acids undergo is, acids undergo a lot of reactions. The ones that we need to be sure of is acid plus ammonia, and it ends up producing an ammonium salt. So it's an ammonium salt. So the H in the acid gets replaced by the ammonium ion. So for example, I've got propanoic acid, which is CH3, CH2, COOH, and I'm going to react it with ammonia. So the H in the acid is going to be replaced by, ammonium ion, CH3, CH2, COO and -1, and in place of the H, there's going to be NH4 plus 1, which is going to be your ammonium ion. So remember these acid reactions, there are four of them, four of the main reactions: metal plus acid, carbonate plus acid, you've got acid plus carbonate, and you've got acid plus ammonia as well. So remember those reactions. So over here we had these two things getting formed. When the ester was broken down by KOH aqueous, the carboxylic acid ended up turning into a salt because it's an alkaline condition. So you're going to write the structural formula, which is in this space, it's going to be the condensed formula. It's going to be CH3. I'm trying to write this one. So it's going to be CH3, CO O -1 and K plus 1. The other one is, let's write the condensed CH3, CH. So if I write this, it's going to be CH3, CH. So I'm going right to left, CH3, CH. You got a branch of CH3, so put a branch of CH3 over here. And then there's an OH. So that's the condensed version. Now this one, what will happen if you heat this molecules, which is this? This is an alcohol. But remember that alcohols, the first thing is, what type of alcohol is this? So we're going to try and figure this out first. So you got a CNOH, and there is CH3, three CH3s around it. Now, when the alpha carbon, or the one with OH, has got it has 3 carbon chains, that's a tertiary alcohol. Remember, tertiary alcohols don't get oxidized. Primary alcohols, they do get oxidized, they turn into aldehydes. Secondary alcohols over here, they do get oxidized, they turn into ketones. Tertiary alcohols we studied, they don't get oxidized. So when you reacted with K2Cr2O7, primary alcohols and secondary alcohols, they're going to get oxidized, but not tertiary alcohol. So over here, there's not going to be any oxidation or no reaction in this case. Then this one, let's talk about this one. This option E, that's a ketone because it's CH3. The middle C is a double bond O, and then you've got another CH3. So that's a ketone. You're reacting it with NaBH4. So what's going to happen? Here's your ketone. When you react it with NaBH4, it's going to get reduced back to an alcohol. So ketones, the reverse happens. They secondary alcohols, they turn into ketones when you oxidize them. But when you have a ketone and you reduce it, it turns back into an alcohol. So this is exactly what you're going to do. I'm going to draw the same molecule, except that in the middle, the C double bond O, I'm going to turn it into an alcohol. That's it. So that's a reducing agent. Then I have a reaction of an alcohol with PCl5. What that does is that the OH gets replaced by Cl. So this reaction, where's let me open the latest one. This one is probably an old one. Just a second. So this is the original board. Now let it load. Now an alcohol, can be turned back. So you're talking about this reaction. We're talking about this thing. An alcohol turning back into a halogenoalkane. So this thing. An alcohol will turn back into a halogenoalkane if you react it with PCl5 with heat, or PCl3 with heat, or HCl with heat, or I mean, you react with a lot of things, it's going to turn back into a halogenoalkane. The OH will get replaced by a halogen. So that's what's going on in this particular case. You reacted with PCl5, the OH gets replaced by, so everything would be the same. It's going to be CH3 bracket 3, and it would become CCl. And then this last one, you're heating it with MnO4 heat under reflux. So that is strong oxidation that's going on. Now we did this in alkenes. Now this is this has two functional groups. It's got an alkene, and it's got an alcohol as well. So first thing, let's focus on the alkene. What happens to an alkene? Like if you look at the revision chart, if you reacted with KMnO4, here's your alkene. If you reacted with KMnO4, the first thing is that the double bond is going to break. And there would be three options. When you react an alkene with, or you do strong oxidation, the double bond always breaks, and you've got three options. Either the double bonded carbon atom had two carbon chains attached to it, then it would turn into a ketone. Or the double bonded carbon atom had one carbon chain attached to it and it had one H, then it would turn into a carboxylic acid, shown over here. Or you had the double bonded carbon atom and it had two hydrogen atoms, then it will be turned into carbon dioxide and water molecules. So you've got these three options, but the first thing is that the double bond has to break. That is what happens in strong oxidation. So let's try and do strong oxidation. The double bond needs to break. So this one, this side, let's focus on this side. It's CH3 and CH. And there's a double bond. So the double bond has broken. This other side, it's got CH2OH. And this side, there's a CH. And there's a double bond. I say anyway, so and we're going to focus on the carbon atom that was making the double bond. What's going to happen to this carbon atom and what's going to happen to this carbon atom over here? Nothing should happen to the rest of the molecule. The only thing that's going to take place would happen with this carbon atom over here. So you've got a double bond. So which one is this? You got a double bonded carbon atom with two hydrogens. You got a double bonded carbon atom with one carbon chain and one H. We have this one. This carbon atom would change into a carboxylic acid. It would change into double bond ON, OH. So we have a double bonded carbon atom, which had one carbon chain and one H. So if you look over here, we had a carbon atom with one H and one carbon chain. So this one will turn into a carboxylic acid. So you turn it into a carboxylic acid, it would become CH3. This particular C will turn into carboxylic acid after oxidation. The same happens to this one. You've got a carbon atom with one H and one carbon chain. You've got a carbon chain on one side. So that will turn into a carboxylic acid. This one over here will turn into a carboxylic acid as well. So it will become serial bond O and OH, followed by CH2 and OH. So that is strong oxidation, heat under reflux. You're heating it with MnO4, that's strong oxidation happening. The double bond splits. You get a carbon atom after the double bond is split, and the carbon atom is bonded on one side by an H and one side on a carbon chain. So this particular carbon atom will turn into a carboxylic acid. The same happens to this other carbon atom that also turns into a carboxylic acid. Is this clear? Abdullah, Alicia? Anna, is this clear?
Yes, sir.
Yes, sir.
But the thing is, it's not just an alkene. We did the oxidation of alkenes, so that's done. This part over here is done. What about it was also an alcohol. This other carbon atom, we left that out. We weren't focusing on that, but you've got this other carbon atom, and that's an alcohol. And it's a primary alcohol. It's got 2 hydrogens, and it's got a carbon chain on only one side. So this one over here is a primary alcohol. So what happens to primary alcohol according to our oxidation chart? A primary alcohol gets oxidized by K2Cr2O7 or KMnO4 to an aldehyde, and it gets further oxidized by K2Cr2O7 or KMnO4 into a carboxylic acid. So primary alcohol, I mean, this is primary alcohol written, it turns into an aldehyde and it gets further oxidized to carboxylic acid. So we left that one. So I'm going to focus on that one. This particular carbon atom over here will turn into a carboxylic acid. So just make it into a carboxylic acid. So these are the 2 molecules that you're going to get once you oxidize this substance. And you have to, I mean, the space is limited, so you're going to write the cadence formula. The cadence formula for this one would be CH3, COOH. The cadence formula for this molecule over here would be COOH, and over here it's also COOH. They're 2 carboxylic acid groups. So it's a dicarboxylic acid group. So that's the result of this one. So let's move to the next table now. He's saying during some of the reaction, a color change occurs. Complete a table, and he's saying color at the beginning, color at the end, and tell what reaction. So one by one, we're going to pick this. Remember KMnO4. KMnO4, you always get a color change. KMnO4 is purple to, it's purple to colorless. Make sure you remember this color change. K2Cr2O7, that's orange to green. That's orange to green. As a tolerance reagent, there's going to be a color change. Remember tolerance reagent, I'm not sure if this is written over here, but tolerance reagent gives you a black precipitate or silver mirror. Okay, so there's going to be a color change. A black precipitate would be formed, and silver mirror would be, I mean, I think I should add this over here. Let me just write this for tolerance reagent. You get a black precipitate and you get a silver mirror. And we can so that is what you get for tolerance. For felling, remember the when an aldehyde gets oxidized to a carboxylic acid, felling gives a brick red precipitate. So we should add that as well to the chart. So you get a brick red precipitate. And for the others, I hope everyone remembers K2Cr2O7 is orange to green and KMnO4 is purple to colorless. Now moving back to the question, so we did that part, the color change part. Let's do the next one. Now you got a formula over here. He's saying there's a substance called X. He's saying treatment of X with sodium metal produces a colorless flammable gas. What does this result tell you about the functional group that could be present in X? So sodium metal. Who reacts with sodium metal? You got carboxylic acids. We did a reaction. Carboxylic acids, they react with sodium metal. Metal plus acid produces salt plus H2. So sodium metal reacts with it. And there's this other functional group as well, which is alcohols. Alcohols have a terribly slow reaction with sodium metal, but they do react. The OH, the H in the OH gets replaced by Na+1. And it's like a metal plus acid reaction. So alcohols also react with sodium metal. So this could be a carboxylic acid or it could be an alcohol. So that tells you it could be both. The other one is there's no reaction when X is treated with hydrogen carbonate. What does the result tell you about the functional group? So it can't be a carboxylic acid. Why? Because we just studied that carboxylic acids do react with carbonates. Alcohols have only one reaction, that's it. I mean, alcohols, the only reaction that they have is with sodium metal, that's it. Carboxylic acid, we just did that. We did several reactions of carboxylic acids as acids. So carboxylic acids do react with this. So that confirms that it's an alcohol, not a carboxylic acid. Because we just studied that carboxylic acids have all typical acid reactions. Then he says X is shaken with bromine and the color disappears. That's a bromination test, and that indicates, hopefully everyone remembers, the test for bromine indicates that there's a double bond. It's an unsaturated molecule. So what information you've got so far? That this molecule is an alcohol and it's an alkene as well. So in the next part, he's going to ask you, is this all clear? I mean, this part. Everyone, is this clear? So it's not a carboxylic acid because it would have reacted with the carbonate. So it's an alcohol and it's got a double bond. So moving to the next part. So we've got X, we figured out X, C4H8, O2. It's got double bonds. That's one thing that we figured out, and it's got OH groups, alcohol groups. So there are two things that are part of this molecule. Now he's saying that the carbon chain is unbranched and the molecule is not cyclic. The first thing, carbon chain is unbranched. So that means the 4 carbon atoms are in a line. So the carbon chain is unbranched, which means all of them are lined up. No oxygen atom is attached to any carbon which is involved in pi bonding. Pi bonding is when double bonds are formed. So let's say I put a double bond here. He's saying that no oxygen must be next to it. So the OH groups must be in some other place. So here's one version of the molecule. Is this C4H8O2? Is this H8? 1, 2, 3, 4, 5, 6, 7, and 8. So a molecular formula is fine. So the second statement is saying that the oxygen atom, where's the oxygen atom in the OH group? Is attached, should not be attached to any carbon atom which is involved in pi bonding. So if you have your double bond over here, then the OH groups must be on some other carbon atom, right? Is this clear?
Yes.
And then no carbon atom has more than one oxygen atom joined to it, which basically means that you can't have 2 OH groups on the same carbon atom. That's the third statement. So how many, he's saying there are 5 possible isomers of X which fit these data. So let's try and figure out another one. Now he's saying there are 5 of them. So let's try and figure out the next one. I can switch the position of the double bond. I can have the double bond over here. And the OH groups, remember that OH groups have to be kept away from the double bond. So that's another one. So that's another one. So I've got 2 possible isomers. He's saying 4 of these isomers exist as 2 pairs of stereoisomers. And you have to draw those 2 pairs of stereoisomers. So out of the 5, 4 of them are basically stereoisomers. So I've drawn these 2. You can try and think of any other. Remember, the double bond has to be away from the OH groups. Now, 4 of these isomers exist as 2 pairs of stereoisomers. So stereoisomers are either optical. So if you look at this carbon atom, this one is chiral. A chiral carbon atom is a carbon atom that's attached to 4 different groups. So all 4 sides around this carbon atom are different. So it's going to exist as mirror images. Remember we did this in stereochemistry, that when a molecule or a carbon atom is chiral, it has 4 different groups attached to it. Then just like your 2 hands, there would be 2 versions of the molecule. One of them would be a mirrored version of the other one. They're going to look similar, but they're going to be different. So I'm going to draw the first one. This one is chiral. So it's got an OH. It's got a C double bond C with 2 H's. And it's got an H over here, and it's got C, OH, and H, and H. So here's your chiral carbon atom. That's the carbon atom over here. That's chiral, which means you're going to draw another mirrored version of this molecule. The mirrored version would be just like your 2 hands. It's going to be a mirrored version. The left and right would be switched. You can just draw it as if you're going to see this molecule in a mirror. So is this clear? The first pair. You think draw each of the 2 pairs. Is this clear? So what about this one? The other stereochemistry that you did was cis trans. That when you have a double bond and when the carbons in the double bond are attached to 2 different groups, and this carbon over here is also attached to 2 different groups, then the molecule, the 3-dimensional shape of the molecule will be, there would be 2 different versions. Around the double bond, the shape of the molecule is fan-shaped. It looks like this. Now this carbon atom, I mean the first one over here, the one that I'm underlying, is bonded to an H and a CH2OH. So it's bonded to an H, and on one side it's bonded to CH2OH. The other one is the same. It's bonded to an H and it's bonded to a CH2OH. That's your cis version. Cis version is that both H's are pointing upwards. You're going to have another version of the molecule where the bonding would be the same, except that the direction of the bonds is going to be different. So this carbon atom over here is bonded to an H and a CH2OH. And this carbon atom over here is bonded to an H and a CH2OH. So it's bonded to an H and a CH2OH. So it's the same bonding, except for the fact that the H atoms are now pointing in. They're pointing in opposite directions. So that's your trans version of the molecule. Okay, is this clear?
Yes.
So just remember, I'll just go through this once more. Okay, the first part said that there was double bond, bromine decolorized. It was reacting with Na, but not with carbonates. Not with carbonates meant it wasn't a carboxylic acid, so it must have been an alcohol. And then he said that he gave us some conditions. We knew that there was a double bond in the OH groups, right? And it was C4H8O2 actually, sorry, which basically meant there would be 2 OH groups. So he gave us some conditions that the carbon atoms would be in a straight line, and whenever there's a double bond, the OH must not be even close to it. It should not be next to it. So the OH must be on the other carbon atom. So whenever you have a double bond, the OH must be on the other carbon atoms. So we did that, and he told us that 4 of them existed as 2 pairs of stereoisomers. So this molecule over here was chiral. So it existed as 2 pairs of stereoisomers. One of them would be this one, the other one would be a mirrored version. And you've got the other one, you got a double bond. So that was making cis and trans molecules. So that was geometric isomers. So let's continue tomorrow. Is this clear, this question so far?
Yes.
Shannon, let's continue tomorrow then, okay? Okay, everyone, take care.
Okay. Thank you.
Hafiz.
No.